Alright, so today the learning target is using p-values to either reject or fail to reject the null hypothesis. We're hoping to be able to interpret a p-value, understand why you would use a p-value, and that you can use it like in a word problem to clarify what you want to do with the statement that's given. And it may seem a little unclear now, but hopefully we'll get to the point where you understand that. Okay, a p-value, when compared with alpha, will tell us whether or not we should reject the null and or the claim. So sometimes the claim is the null, sometimes the claim is the alternative, and you want to make an assessment on the claim. So a couple little notes here. P, in this case, should always be a capital P. Lowercase p is going to be a population proportion. That's not what we're talking about here. This is alpha. Alpha is your level of significance. It's also your the chances of a type 1 error also, but we're not going to get into type 1 and type 2 errors today. Alright, so p-values. P-values are the probability, or p is the probability of finding a statistic as extreme or more extreme than the one from the sample data. That is to say, if I believe something to be true, if a cereal company claims that we have 24 ounces in every 24-ounce cereal box, on average, if I took a sample of their cereal boxes and got my sample average to be 22 ounces, a p-value would tell me what is the probability of finding a sample with a 22-ounce average or less, if 24 is true. Okay? It is found by following kind of these 4 steps. You find the standardized test statistic. That is going to be this formula over here. X bar, remember, is our sample mean, so whatever you get from your sample. Subtract mu, your population mean, divided by sigma over the square root of n. Sigma is our population standard deviation, and the square root of, and n is our sample size. One thing to note, if n is greater than 30, use S, the sample standard deviation, to estimate sigma. So we can kind of take this sigma out and put an S in as long as our sample is greater than 30. Once you're going to do this, you're going to sketch the distribution. With these problems, the distribution, or the shape distribution you sketch, should be normal, or approximately normal. Okay? So you're going to assume an approximate normal distribution, and the problem should state that. Then you're going to use your standard normal table and the test statistic. Remember, our test statistic is just a z-score, to find a critical value. Okay? You're going to multiply that critical value, to find an area to the left of your critical value. This can also be called your critical value here. Then you're going to multiply that area, multiply your area. If it's a 2-tailed test, if it's a 1-tailed test, that area just becomes what you have. Okay? So what you have here, guys, is a statement that if the p-value is low, you're going to reject the hoe. It is as easy as remembering that, and every one of you will remember that. That's how my stats teacher told me. That's what it comes out to. Nobody ever forgets it. Because you're coming up with this value and you're comparing it to alpha. So if I have a p of 0.04 and an alpha of 0.06, then p is lower than alpha, I reject my h sub o. Okay? So you have, if the p is low, you're going to reject the hoe. And it's that easy. You're going to remember it on any test you take. You'll probably remember it when you go to college. It may sound weird in a lecture hall of 300 people yelling that out when the teacher asks you what to do with p-value. But feel free to. You'll make everyone laugh. So let's take a look at an example here. Alright, so in this example, a manufacturer says that a new model has an average miles per gallon of 30. A random sample of 32 of these cars was selected, and that sample had a mean of 29.3 and a standard deviation of 1.4. At alpha equals 0.05, does the manufacturer's claim appear to be true? We've got different variables in this case. Let's switch colors for a sec. Here. What is 30? Well, 30 is what they're claiming to be the actual average. That is mu. Whereas 29.3 is the average of the sample, so that is x bar. This is nice and easy. It tells me alpha equals 0.05, 32 equals n, and 1.4 equals s. Now the combination of these two variables is going to tell me what? That I can use s to estimate sigma because n is greater than 30. So, first step, state the null and the alternative hypothesis. My null hypothesis is that h sub o of mu equaling 30. H sub o is mu equals 30. That was the hypothesized or the claimed average. That makes h sub a, mu does not equal 30. Now one thing to notice is that I didn't write this up here, but this one is the claim. So in this case, if I reject the null at the end, I am going to also say that your claim is untrue. If I reject the null, that's saying this isn't true. That means the claim isn't true. However, sometimes we see the claim on the alternative. So if I reject the null, but the claim is on the alternative, rejecting the null provides evidence to support the claim if the claim is the other one. Alright, so the second step is to find our standardized test statistic. We said that it was this formula here. That bar kind of went away. X bar minus mu over sigma divided by square root of n. Now, I substitute in, and that gives me 29.3 minus 30 divided by 1.4 over the square root of 32. Type this in your calculator. When you use a calculator to do this, you do want to put parentheses around here and parentheses around your numerator. Type it in all as one line. It will prevent you from making some of those errors where your calculator is following PEMDAS and you're not quite putting it in right. So, when I put this in, I get negative 2.83. When I get a z-score of negative 2.83, I'm going to take and I'm going to look that z-score up in the in the standard normal table. When I look that up in the standard normal table, I get 0.0023. Since this is a two-tailed test, I double the value to be 0.0046. What I didn't do, and I should have, is to sketch my distribution. I know that this is my mean of 30, my hypothesized mean. I know that I got an observation of 29.3. So my observation was 29.3. My hypothesized mean was 30. This gave me a critical value of negative 2.83. And because this is equal to, the hypothesis is that it's equal to. It's not that it's equal to or bigger. So if I got something way out here, if I got an observation, a sample way in the tails of my distribution, then I could potentially reject my null. Well, the question is, how big is this tail? This tail is 1/2 of alpha. And this tail is 1/2 of alpha, such that both equal alpha. And we know alpha is 0.05, so that the actual area would be 0.025 in each tail. Now, once you have your p-value here, guys, all you're going to do is compare p to alpha. P equals 0.0046, alpha equals 0.005. The question becomes, what's the relationship? Well, 0.05 is greater than 0.0046. Remember, the p-value tells me the chances of getting an observation as extreme or more than this test sample. Okay? So the chances of getting a sample that has an average of 29.3 is 0.46%. I think we would all agree that that is very unlikely, right? 0.46% is the percentage of samples that would have an average of 29.3 if your actual average was 30 and this was your standard deviation in sample size. Since p is low, I am going to reject my h sub o, and that's going to come in my interpretation piece. So I interpret the result now. Since p is less than 0.05, it is unlikely that we would get a sample mean of 29.3 just by chance. So we would reject the null. I would say that the miles per gallon is not likely 30 miles per gallon for that type of car. That is how you would use a p-value to interpret a problem such as this. So if you're given the p-value, the mu, everything like that, you're going to use it like this and come up with this interpretation.